Welcome back everyone. Today we are diving into an important concept in C# programming, local state and shared state in threading. Understanding these concepts are crucial for writing efficient and safe multi-threaded applications. So without further ado, let's get started. Local state refers to variables that are confined to a single thread. These variables are not shared between threads, which means each thread has its own copy. On the other hand, a shared thread involves variables that are accessible by multiple threads, and then multiple threads access and modify the same variables. We must be cautious. Without proper synchronization, this can lead to race conditions where the outcome depends on the unpredictable timing of threads. In this example, as you can see, I have two threads, a worker thread and a main thread. At first, I'm going to create a new worker thread and pass T1 as an argument. Therefore, for 1000 times, I'm going to write T1. After that, the main thread calls the print method with the MT as an argument. And for 1000 times, it's going to write MT. So let me draw the process structure again. As you can remember, we have code, we have memory, we have stack and heap, and a main thread. In this example, the main thread will print MT. In the first line, I'm going to create a new thread with its own stack, and it's going to write T1 for 1000 times. And because we have context switch between these two threads, I expect to see something like T1 for a couple of times, and then MT, and then T1 for a couple of times again. So let me run the project to see what's the response. As you can see, we have MT, and then we have T1 again, MT, and then T1, and finally MT. So let's see what's really happening. Considering that this is my main thread, and because the variable index is a value type, I'm just going to draw a stack. For 1000 times, index increases from 0 to 1000, and in each iteration, it's going to write the input value. For the main thread, it is empty, and for the worker thread, we have exactly the same behavior. In the stack, the index variable is going to iterate from 0 to 1000 times, and in each iteration, it's going to print input value, which is T1. At first run, suppose that the main thread has enough time quantum, and it's going to write empty 2 times, and suddenly they have a context switch because its timing has completed and it's time for the worker thread. The worker thread is going to print the T1 a couple of times until its timing is finished. Then we have another context switch to the main thread, and the main thread will continue until its timing is completed. This story continues, but suppose that the main thread has run until line 9, 10, and suddenly at line 11 we have a context switch, and it's time for the worker thread. Worker thread continues its work, but how does the CPU knows where was the previous status between each context switch? As we said before, we have a PC, which is like a GPS for your CPU. It keeps track of where the process is in its instruction sequence. Think of it like a snapshot of the CPU's brain. So that's how the CPU knows where was the previous status between each context switch. It's important to note that you can change the priority of threads by altering the value of the priority property. It allows you to adjust the priority from the highest to the lowest. It can be useful in scenarios where you need to prioritize a specific thread. Now let's take a look at the shared status example. In this example, as you can see, we have a local variable index, which is a local state variable, and it's inside the print method. But we have another variable called is finished, which is a shared state variable because it's outside of the print method. Let me draw the process again. As you know, we have code, we have memory, main threads, stacks, and heap. Here at line 18, we are going to create a new thread, which is our worker thread. It has its own stack. An index will be saved in the stack as it's a value type and it's a local variable. But isFinished is not in the scope of print method. So it's a shared state variable and it's a value type. It will be saved in the stack of the main thread, which is the parent for all the threads. Initially, its value is false. When the main thread starts working at line 9, it will change its value from false to true, and it will iterate 5 times. But we have a context switch. So for instance, after printing 2p, we have a context switch, and now it's time for worker thread to start working. Worker thread starts working, but the isFinished value has changed and it is true at this time. So the if condition is not correct anymore, and it means that the worker thread will finish its work. Again, we have another context switch, and now it's time for the main thread to continue its work, and it will print the remaining 3p because we have to iterate 5 times. Just as a quick reminder, in the heap we had a place called the high frequency heap. A variable inside high frequency heap is shared among all these threads in the process. Each worker thread, as I said, has its own stack and heap, which are completely isolated, but high frequency heap is shared between all these threads, and it's highly recommended that all the variables inside it must be read-only, otherwise it's possible we have a racing condition. Let's run the project to see what's the result. As you can see, we have p 5 times, which is expected. Now let's take a look at another example. In this example, as you can see, 10 times we are going to create a new thread. Let me draw the process structure again. We have code and memory. As you know, we have stack and heap, and we have a main thread. Based on the code, as you can see, the value of the index at first is 0. So in the first iteration, it's going to create a new thread. It's not going to run the thread. It is just going to create a new thread, and as the time quantum for the main thread has not been completed yet, in the next iteration, value of the index will be 1. So it's going to create another worker thread, and in the next iteration, the value of the index will be 2. And again, it's going to create another worker thread, and it continues until we have a context switch. Now it's time for the first worker thread. It's going to write the value of the index as its shared state variable, and the value of the index at this point is 2. It's going to print 2, and then it's completed. This time for the other thread, it's going to write the value of the index, which is still 2. And the same story goes on until the time is for the main thread. Now in the main thread, we're going to have another iteration. We have exactly the same story again. So the output value would be something like 8, 9, 9, or something like that. Let's run the code to see what's the result. As you can see in this example, we have this value, which might be different on your computer, but this is the expected result as we explained. To sum up, local state is easy to manage because each thread works with its own data, while the shared state requires careful synchronization to avoid race condition. By understanding and properly managing these states, you can write efficient and safe multi-thread applications in C#. If you found this explanation helpful, don't forget to like, subscribe, and hit the bell icon for more programming tutorials. Thanks for watching, and happy coding!